Good morning, students, and welcome to the session of Harmonic Resonance, that is under Unit 4 and under subject Power Quality. Resonance plays very important role in harmonic because at harmonic frequencies there is a shooting up of the amplitude like voltages, currents, and that is called resonance. So before going to study harmonic resonance, let us have a look at what is the concept of resonance or what is the resonance itself. In order to explain resonance, I would like to take the example of soldiers who are performing parade near to the bridge. Let us assume that some soldiers are there and who are performing parade near bridge. Then when bridge comes and when they want to cross the bridge, then they will not perform parade under this situation. They will disperse because the reason is if the frequency of vibration of bridge matches with the frequency of feet of soldier, then there may be resonance and the bridge may collapse. This incident took place in Second World War and that is called resonance. Therefore, resonance can be defined as matching of frequencies of two systems. So when two systems frequency are identical, then there is a problem of resonance or phenomenon of resonance. In electric circuit also, resonance is of matter of concern and resonance is divided into two types, that is series resonance and parallel resonance. Obviously, the resonance that is taking place in circuit is a series resonance. At the contrary, the resonance which is taking at parallel circuit is a parallel resonance. Let us study series resonance in initially. What is the concept? If the series RLC circuit is there where R, L and C are connected in series, therefore the current is common and there is a division of voltage. So in that case, there are two components. One is XL and another is XC. Assuming that R is not there, 0. Considering XL, that is the inductive reactance, XL we know is 2 pi FL or 2 pi omega L, or simply in terms of omega we can say that if I plot frequency versus reactance, then I will get a straight line because x is equal to 2 pi L or x is equal to omega L is linear between XL and XC. It forms a linear relationship between XL and XC. So this is called a positive slope. This slope, which is starting from 0 and going onwards, is called positive slope, and the positive slope indicates that the power factor is lagging or the circuit is lagging. Now this is regarding XL. Now we know that XC is equal to J upon omega C. If I multiply and divide J on both sides, I will get minus 1 upon J omega C. So minus sign indicates that the slope is negative, and minus sign also indicates that the power factor is leading. So in this way we get the curve like this, which is to some extent reverse characteristics, and that is going inversely between XC and F. So in this way we have got two curves. One is XL curve, which is lagging and the slope is positive. Other is XC, which is leading and the slope is negative. They have got the same common frequency of F, but they have got different uh, coordinates on y-axis. One is XL and other is XC. Now if I combine these two curves together, being keeping frequency same, then I will get this type of graph, which can be an intersection of the curves of XL and XC, as you can show here. And XL and XC will intersect each other to some point. So the frequency at this point is a resonant frequency. So how do you define resonance? Resonance is a frequency at which XL and XC is equal, or XL is equal to XC. So this is the simple condition of resonance, particularly series resonance, where XL and XC are equal. Now they have got comparison with FR, that is resonant frequency. So in the first case, we can see here that FR is at the left hand side of FR. The condition is F is less than FR. So this is called capacitive circuit. The circuit is capacitive, or there is a leading uh, PF under the condition where F is less than FR. In the second circuit, the frequencies are more than FR. So here the circuit is inductive circuit, which is a lagging PF. And the middle one, where F equal to FR, is a resonant frequency. So these are the three conditions of frequencies uh, as compared to the resonant frequency FR. Now here, as we know that XL is equal to XC, we can replace XL as 2 pi FL, and XC is 1 upon 2 pi F into C, or FR into C, because it is a resonant frequency. The condition of XL equal to XC occurs when the two frequencies are same. Therefore, we will get here that FR square is 4 pi square into LC. Therefore, FR is equal to 2 pi root LC. So, we can call this as omega R, that 1 upon omega C. So, in this way, we get relationship, very important relationship, that the resonant frequency is 1 upon 2 pi under root LC. Now, Z is equal to R plus JX. We can expand X as XL plus XC, and if you take, we know that XL is j omega c. So it is j omega c plus X is 1 upon j omega c. Again, if I multiply and divide by j, I will get minus j omega c. If I take these as cancellation terms, because we know that at resonance these are equal. Therefore, because of cancellation, only R is available, and the circuit becomes pure resistive. So it is very important to note here that at the point of resonance, XL is equal to XC, and therefore only R is there. There are no XL and XC. Means the circuit is purely resistive. And we know that when circuit is resistive, when the power factor is unity, or the phase angle between current and voltage is 0. Therefore, negative angle indicates leading PF, and as R is less, Z is less, and therefore current is more. So because of R and no X, power factor is unity because it is a resistive circuit. Phase angle is 0, and voltage and currents are going hand in hand, that is, they are in phase with each other. So what will happen under this condition at resonance? That when R is lesser, the current will have tendency to flow through R, resistance R, because the current will find resistive path to flow across, and it will be flowing through resistance R. Therefore, maximum current will flow, and the current will be maximum, and the Z will be minimum. So this is the condition of series resonance, that at series resonance circuit is resistive, XL XC are 0, So being R only, it behaves as a pure resistive circuit, and therefore at pure resistive circuit the power factor is unity and the phase angle between V and I is 0. So in this way these are the conditions of series resonance which you must remember from exam point of view. Even the design of filter depends on the design of capacitor or design of concept of resonance, series and parallel. So in this way at resonance, as I told you, impedance is minimum, current is maximum, and the phase angle is 0. Power factor is unity. So in the first diagram where we can look, if I plot X impedance versus frequency, then I will get that at resonant frequency, impedance is minimum. If I plot current versus frequency, I will see here in second graph that current is maximum at resonant frequency. And the third diagram, if I draw phase angle versus frequency, then phase angle is 0 at resonant frequency. So in this way, these are some criteria for frequency. Now here we can see that here XL is equal to XC, and here there is a mismatch between current and voltage. Here it is capacitive because XC is greater than XL. Here it is inductive because XL is greater than XC. Here again it is dividing the circuit into two parts, positive and negative, and here also it divides into two parts, positive and negative. One part is capacitive or leading, and other part is inductive, that is lagging. Now coming to the bandwidth depends on resonance. We have seen that in series RLC circuit, bandwidth or XL is equal to XC. This condition is there. So the difference between lower cutoff and upper cutoff frequency is a bandwidth, which is 0.707 times Im. That corresponds to maximum power flow. So bandwidth is the difference of FH minus FL, where H is upper cutoff or higher cutoff frequency and FL is lower cutoff frequency. Therefore, bandwidth is obtained by the ratio R upon 2 pi L, where the lower cutoff frequency FL is given by FR minus BW upon 2, that is bandwidth upon 2, and the upper cutoff frequency FH is given by FR plus bandwidth upon 2. So these are the concepts of series resonance and resonance in particular. Next time we'll have discussion on what is harmonic resonance. So thank you very much for watching. We'll resume the topic of resonance in our next video, that is video number 10. So thank you so much. Thank you for watching.